This final session on spatial information aggregation will be discussing logistic regression. Logistic regression can basically be seen a bit as a unifier of the ideas in the previous session, and particularly on weights of evidence and the probability aggregation. There's a really good book on logistic regression by Hosmer et al. And I'll also be discussing two applications related to geology. One is on detecting facies from seismic data, and the other is on the application again on landslide susceptibility analysis. So now we are applying logistic regression instead of weights of evidence. So here's a typical problem of a regression or a logistic regression. In logistic regression, we typically look at binary output, or at best say categorical output. And so here's a case, say, where you would like to correlate coronary heart disease with age. So expect, of course, that people older are more prone to have such heart disease. But if you look at the dispersion of this data, then it's clear that it's not sort of easy to fit a line, or how should we start summarizing this kind of information. Let's then look at cutting up the problem a little bit more. Let's, for example, put people in age groups. So we have several age groups here in this table, and we count, and then we calculate the expected value of the mean. That means just counting the amount of people. For example, here we see we have only 1 person out of 10, so the mean would be 0.1. Here we have 6 person out of 13, so you see that that mean is going up. And so if you then plot age versus the expected value, which is also can be considered a probability, right? Because we're just counting totals, then we notice that some kind of an S-shape appears. And we've seen this S-shape before when we were talking about logistic function and logits in the previous session. So how are we going to model such distribution? We'll be modeling like in regression, we'll be modeling the conditional expectation of y given x. And so the way it's going to work is that we'll be using a logistic distribution. So specifically for a logistic regression, this means that we're going to model this conditional distribution here in this form. And the reason why we do that is because if we looked at the previous slide, then that S form is typically removed by a logic transformation, and so we get by this logic transformation here. Remember, this is a ratio of basically is again an odd ratio. We take the log of this odd ratio. We get a function of x. So x being what you condition on. This is now age, and we get this linear model. So that also means that we don't have to discretize the variable x. We could just use it as a continuous variable, fit a linear function. And when that function is fit, then go back here and calculate the conditional expectation. So what are the differences with a linear model of regression? So in a linear model of regression, we are regressing and under certain assumptions, for example, on the assumption of Gaussian distribution, etc., we could assume that our regression, least square regression, comes out with a conditional expectation. That has, of course, the assumption that the error that we have is continuous in nature, it's not discrete, that is Gaussian distributed, and therefore that y is also Gaussian distributed. Then we can make that interpretation of conditional expectation. When we're dealing with a logistic regression, it's of course slightly different. In this case, we can only have two outcomes, which is either the outcome is either 1 or 0. So that also means that the error can also have only two possible outcomes. And so that y now has a binomial distribution with this expectation. So it's clear that we can apply the least square formulation to this whole thing, simply because the error is no longer Gaussian, and certainly y is no longer Gaussian. So we can fit by means of least squares. So instead of using least squares, we're really using another idea, which is called maximum likelihood estimation. Some of you are familiar with this idea, but I'll just briefly go over it for those who are less familiar with likelihood models. So a likelihood is essentially an expression of the probability of the observation given the model variables. So in this particular case, there are only two model variables, beta 0 and beta 1. So imagine now that I choose a particular value for beta 0 and beta 1, then I'd like to know how likely is it to get the observations that I'm getting. Well, in this particular case, it's quite simple because once I have a beta 0 and a beta 1, then I can also calculate its probability for any x, that's the pi of x or the expectation. That would be this value. If, however, the observation is 1 minus pi of x, then this would be then the probability so if the observation is 0, then this would be the probability of that observation under x would be this model. So I have to choose, basically, I have a pair x, y. If y is 1, then this is my likelihood. If y is 0, then this is my likelihood. And so one way of writing that for one observation is in this particular form, because then I get 1 minus 1 would be 0, or this is 0, then this becomes 1. So I assume also independence of the observations. So if I would like to know the complete likelihood for all of the observation, not just one here, then I'll just make the product. So this form here is essentially the likelihood observation under the model. It would have been better for the authors to write here explicitly the beta values, because of course this term here is function of beta. So once I have that, I have a function of beta that I can maximize. And so that will be then our maximum likelihood expression. So to do that, typically we take the log likelihood, but even if we take the log likelihood that there's a product into a sum, we still don't get a nice closed form expression. We still have logarithms in there of parameters. So we'll have to do this by iterative solving. That means calculating the derivative of the likelihood function, setting that to 0, and then maximizing that equation, or minus the log likelihood. Often we end up minimizing an equation. So in other words, there's no nice solution as we have in least squares. We have to do a little more computing work. So I'm not going to go into technical details of the iterative solvers. That's pretty standard. I'd like to discuss more what you would get as an output from softwares that you'll be using. And so those different softwares are going to report you different things. And I'll give you a few examples. So of course, what we get here is output for the estimated beta 0, which would be this value here, and the estimated beta 1. Just like in least squares, we can also calculate standard errors. As you know, in least squares, under the Gaussian distribution, we can calculate the standard errors of the regression coefficients. This can also be done in maximum likelihood. Again, it has to be done numerical, and it has something to do with the derivative or the Hessian of the likelihood distribution, which is actually called also the information matrix. Because if you're doing minimization or maximization, then what happens in that maximum, the stability, let's say, of that maximum is important in terms of your standard errors. So I'm not going to go into that. That's actually rather complex theory. Refer to the pages 37, 38 by Hosmer, and there's also the famous paper by Rao on maximum likelihood estimation, which is sort of a classic paper in statistics. So once we know these two coefficients and their standard error, we also would like to know, okay, are they significantly different from 0? And so there we have to invent, of course, a statistic, just like we would have for least squares, and also some kind of significance level. So here we notice that the significance level is very high, and that sort of makes sense because we have a small standard error on this small number, reasonably small standard error on this big number, so it's reasonably expect that these will be not equal to 0, and so they have an effect, the mean effect and the age effect. So how does such testing for significance work? So in this case, we'll try more of a relative approach. We say we're not going to go for an absolute goodness of fit question, an absolute measure, but some kind of relative measure, namely, how does a model perform that includes the variable versus a model that performs without including the variable? So for example, in a linear least squares, I could say, what if I just use the mean as an estimation versus actually the model that I'm using? That's shown here. So in linear least squares, we could say, how does the prediction compare to just using the mean? So this is called the sum of squared regression error. So this means there's two parts to it. One is calculating, here. One is calculating the deviation from the mean, and this is the deviation from the model. So if the deviation from the mean is 0, then everything is error is in here. While if the deviation from the mean is very large, then we may get an improvement by adding the model. So in a logistic regression, of course, we can't calculate differences because we're dealing with binary outcomes. And so we're working with the likelihood. So we ask the question, what is the likelihood of the fitted model versus the likelihood of the saturated model? In the saturated model, you would use, say, as many coefficients as data. In many cases, though, one often just takes the likelihood of the saturated model just to be constant or 1, and so that would disappear out of that term, so we don't have to calculate this. In particular, this would be impractical if you have many observations. So then there's the equivalence of the SSR, which is the deviance. And so the deviance can also be written in this particular form. The deviance is sometimes used in testing significance, likelihood ratio test, but we'll use another type of method, which is called the Wald test. So in the Wald test, we ask ourselves, are the beta coefficients significantly different from 0? So we make the null hypothesis that the beta coefficients are 0, and we calculate what is called this Wald statistic, which is basically the estimated beta over the standard error of beta. And so that sort of makes sense, right? So we expect that if beta is very small and standard error is very large, then this Wald statistic is going to be very small. And then under certain circumstances, under null hypothesis, we actually assume it's a standard normal distribution. And so we can then just do statistics like with calculating doing hypothesis testing with the classical Z statistic, as it says standard normal distribution. So for example, if you take this number divided by that number, you get this number. So that's for the normal distribution. Of course, it's a very high number. And same for the constant is a very high negative number. So it's unlikely that that the hypothesis, so the hypothesis null hypothesis can be rejected. In the same sense, then we can also build confidence intervals. So typically what comes out of the software is that we also get the standard errors. Besides the standard errors would be this number and that number. We also get the covariance between the two. So if you divide that by that, you get the correlation between those two. And so from that, we can then develop confidence intervals based on this. And then we have an estimated function g, and so we can also look at the variance of g as the variance of beta at 0. Then of course we have, because we have x, it becomes x squared, and then 2 times x, the covariance. So then the extension to multiple logistic regression is then also quite straightforward. So instead of having a simple model as before, we have now multiple variables xp in our regression function. Sometimes, so x here is assumed to be some kind of variable that has a scale. It could be 1, 2, 3, 4, 5. It could be continuous, but in many cases, of course, we have to deal with variables that don't have any scale. So for example, race would be a good example of that. And so in all these methods, the way we address that issue is by including what are called dummy or design variables, sometimes also called indicator variables. They are basically variables that are 0 or 1 that will allow us to model variables such as race, shape, white, black, Caucasian. So white, black, Asian would then be would regard in 2 dummy variables indicating what race we're dealing with. So otherwise, everything sort of works the same way. Here's just an example of osteoporosis in women. And so there's a number of variables such as age, weight, so osteoporosis, of course, leads to bone fracture, the prior fractures one have, whether it's menopause or not, etc. And so then we can calculate again the logistic function, the heuristic model, by calculating the various coefficients, their standard errors, and looking at the z statistic. So we notice that a few of these z statistics are high, which means that they're very significant, and some of them are low, and so they are much less significant. And then we have confidence intervals, and of course you notice that unsignificant values have confidence intervals that include 0 as the value. Okay, so then the application of logistic regression to a landslide case study would be quite straightforward. So now we have a number of, as before with the weights of evidence, we have a number of parameters. So now what's really nice about this is we don't have to discretize anything. We can just use them directly. And we have these independent parameters, and we have some landslide inventory base with possibly different types of landslides. So here's another type of output of logistic regression. That's why I put this in. It depends a bit on the software you're using. So here is reported -2 log likelihood. That was before. And so if we divide that by L0, then we get this deviance. And so we want this number to be high, and we want this number to be low. And that difference, if they were relatively the same, then that would mean that the model doesn't predict anything more than the saturated model. We can also, what also we could do is simply look at the predictions. So we could say create a map here of probabilities, and then compare those probabilities to the actual landslides. Pointer's back. And so one is some kind of measure of goodness of fit, chi-squared. There's also other, I'm not going to go into that. There's some other measures that do the same. And so you want this to be very close to 1. So typically, if this number is some 0.5 to 1, then this is typically a good number. So this is basically based on, again, a comparison of the Boolean map, the map I showed you in the previous case, with the probability map and measuring the difference. There's an interesting extension in logistic regression in a nonlinear case that is actually related to neural networks. So in general, a neural network is a regression model that aims to, say, provide a nonlinear function between some independent variables x and some target variables y, just like any regression models would have a set of parameters. So in the next slide, I will show you what that function looks like. It's sort of a graphical model. In that graphical model, as we notice, and this is the equation of that graphical model, is that we make linear combinations of the input. So this would be sort of the typical linear model for either logistic regression or for the linear model in the linearly squares. Then we have a t here, which is again a logistic function. And then we linearly combine this t into an output function. And so what we get here is that we try to model the relationship between x and y using this type of function. As I mentioned, it's easier to explain this with graphs. So in a neural networks, basically we have a set of input variables, so it's just like the variables we had before, and a set of target output variables. So if you just want to do nonlinear regression, then you would basically try to fit the weights that are in this network. So what are these weights? Well, in the previous slide, we saw that we had weights that are linear combinations of the input. These were the W weights, and then we had a function applied to that part. That was our T function, a logistic function, and then we did again a linear combination of those T functions. We sum that up and we get a value of Y. So if you just do regression, then basically you can do least square regression. You formulate a least square problem. You minimize the difference between the the y as modeled through the network, that's a function of theta, and any observations you may have. And so one of the nice efficiencies of the neural network is that optimization is relatively fast due to the graphical nature of this network, is that you can sort of propagate errors back and forward relatively easy, and therefore run optimization methods relatively fast. So now we could say, okay, what if now this output y is binary? And so what I'm really interested in is the conditional expectation, or the probability that as y is 1 given x. So that would then be another type of function. So in that case, we replace the sum here at the end with the logistic function, just like we replaced where we added that logistic function into our standard logistic regression problem in the linear case. So if that's the case, then we can just fit this network again. Now we are not going to fit the network using these squares, but we'll fit the network using, again, maximum likelihood estimation. So then the various weights are estimated in that sense. The only thing, of course, is that in previous case, we could somewhat interpret the weights because we had a linear model. Now it becomes much more difficult to interpret those weights, although in the neural network literature, there are a number of techniques and methods for you to do that. So let's look at an application of that. Here we have a case, say it's an illustration of what would happen if you would be doing predictions in the subsurface. So imagine the subsurface. So basically what we're looking at here is depth. In the subsurface, we have some unknown sand shale system. And the only thing we have about that subsurface is geophysical data. So this is, for example, seismic data. Now, what seismic measures is not where the sand is, but it measures where the contrast between sand and shale is. So, for example, here we see that it goes from white to black. And so this line here, this intersection is basically has to do with the contrast that is appearing here. So this essentially is saying there's a boundary there where we have a change in geophysical properties, and particularly velocity or impedance. So the other thing we have, of course, in the subsurface are wells. So the wells we can actually record for those few locations. We record whether we have sand or shale. So the question is, can we predict the system, at least come up with a posterior probability of sand and shale based on this geophysical data, and then possibly can use that later in more geostatistical modeling. So the way that is done is understanding indeed that your geophysical data is not sort of doesn't have any point correlation with observation of sand. What we have here is that geophysical data is essentially due to a reflection of a boundary. So instead of trying to correlate a pixel that we have in our geophysical data with a pixel of sand or shale occurrence that we have in our well data, we're going to try to correlate that observation in our well with a series of pixels, essentially in order to measure the contrast, in order to essentially capture that pattern that we notice in the geophysics, and try to relate the pattern that we observe in that vertical window to the sand shale observation. So the data here is now, again, a binary y, and the x is now essentially a window of seismic amplitude information collected along that window. So if this window would be, say, size, I don't know, here, 13, then you would have 13 amplitude information. So now we have an x and a y. We can scan the entire well data set for all the possible observations we can have for y and x. And so the idea is then to build a regression model such that when I have that regression model, I can apply it elsewhere in the system where I don't have wells. And so I can predict the posterior probability of having sand. So in this case, we'll use that neural network model. And so this is then what we get. So here we see the true reservoir, and here we see that posterior probability as estimated through the neural network. And you see indeed that we see that it does resolve to some extent these large-scale features. The smaller scale features, of course, it doesn't resolve as well, simply because the geophysics or the seismic has a limited bandwidth, and so it will not be able to pick up all the details. If we take a classification, here we classify, say, just by cutting off at some percentage, then we get a classification model. And here we have the misclassification. What's more interesting is this here, because this can then later be used, and we'll see that in the last part of the course on geostatistics, that this can then be used as a way to constrain geostatistical models using these kind of probabilities.